Hello and welcome. In this video, I want to take a look at the notion of a vector field. I would say that I'm introducing you to the notion of the vector field, but we have actually worked with vector fields in the past, although we didn't necessarily call it that. That is, in Calc 3, you came across the notion of the gradient. As you remember, the gradient had little vectors pointing in all sorts of directions. That is a vector field. So here's the general definition of a vector field. A vector field in R2 is an assignment of a two-dimensional vector f of xy. Notice the little vector symbol on the f to each point xy in a subset of R2. So you give me a point xy in the plane, and I will assign you a vector. You give me a different point, I'll assign potentially a different vector. Right? So for every point in the plane, a vector is assigned. Likewise, a vector field in R3 is an assignment of a three-dimensional vector to any point in R3, at least within some subset of R3. Now, this is very similar to a couple of things we've done in the past. That is, first of all, in the beginning of Calc 3, we looked at what we called vector functions. That is, you gave one variable of input and you got two or three variables of output. You got a vector out. Right? So this is similarly going to be giving you a vector out, but instead of just one variable in, we have two or three variables in here. And of course, we could do this in higher dimensions. For a vector field in R4 is for each point in R4, you're assigned a four-dimensional vector. Okay. I point out here that these vector fields are situations where you have the same number of variables out as in. So you put two variables in, you're getting a two-dimensional vector out. You put three variables in, you're getting a three-dimensional vector out. And this is similar to something we've done earlier this quarter, in that when we were doing substitution of variables within double and triple integrals, we were taking x and y out and we were putting r and theta in. That would be sort of the polar transformation, right? And we did in double integrals. So that was two variables being replaced with two variables. For each r and theta, you could calculate an x and y, or vice versa. Likewise, with triple integrals, we did something like spherical coordinates, where you would have rho, theta, and phi replacing x, y, and z. So for each rho, theta, phi, you got an x, y, z, or the other way around. Right. So those are also, in a sense, they were vector fields, but we view them in different ways. And that's really part of what Calc 4 is doing, is that we're going to, at least this last half of the quarter, we're going to be looking at these multivariable vector functions. You're going to put multivariables in, and you're going to get multivariables out. In the case of vector fields, the number of variables in is the same as the number of variables out. Okay. Now, the way that we visualize them when we're thinking of them as vector fields is we draw little patches of the plane with a bunch of little arrows, right? So here's a very simple example where for each point in the plane, for each x, y you give me, I'm giving you the constant vector 0.3, 0.4. So every single point on the plane is being assigned the vector 0.3, 0.4, and it's drawn here in this picture. I think I can make this picture go live. So yeah, there's the same picture we just had. Now, with a constant vector field, every point is being assigned the same vector. But if it's not a constant vector field, then you see different things happen. So for instance, if I change this 0.3 to 0.3x, then we suddenly have something that looks very different. You give me a point, say let's look at the point 1, how do I want to do this? Let's go with 2, 2, right? So at the point 2, 2, the y-coordinate is still 0.4, but the x-coordinate is now going to be 0.6 because it's going to be 0.3 times 2. So you can see here from 1, 2 to 2, 2, we stretched in the x direction, but it's still the same y component. It's still vertical component there is just 0.4, but now the horizontal component is 0.6. And likewise, as the x gets bigger and bigger, that x coordinate changes. Or you could do something even different, like say 0.3y, where now the vector is changing as the y-coordinate changes. And again, it's only the x-coordinate of the vector that's changing for each change in the y-coordinate. And you can do all kinds of things. Let's jump back over to here. So here's another example of a vector field. This is quite a bit more complicated, but still reasonably simple in that the formulas here aren't too bad. So the vector that I'm assigning to each point xy is calculated by the x component of the vector is x minus x times y, and the y component is just x minus y. So x minus xy, x minus y. And it looks something like this. Now I should point out that I'm not actually drawing this vector field to scale, in that there's a little scale factor down here and I have it at 0.1. If I drew it to scale, it would look like this. This one has a scale of 1. That is, each vector is drawn at the point that it's supposed to, or it's supposed to be, but now it's drawn in its actual length. And the problem is, they get really hard to see what's going on when the vectors are so big. So quite often when we're drawing these vector fields, we have a scale factor. We say, all right, at least we know what direction things are going in. And so for instance, if I move up here, this one, I'm not seeing the true length of the vectors, but I'm at least seeing a relationship. I can see that the vectors are shorter down in around here and they're much longer out in these regions. Okay. I want to show you also an example of a vector field in 3D. So this is CalcPlot 3D doing this one, the two-dimensional one I was using GeoGebra. Vector fields in 3D get really hard to draw and really hard to see what's going on. The ability to have it done on a computer so that you can click and drag and view it from different angles really helps to get some sense of what the vector field is doing. There's just, you're trying to draw way too much on a flat plane. But this vector field is, of course, it's for each point in space, x, y, z, it's outputting a three-dimensional vector. So the first component of the vector is the y component of the spot you're at. The y component is the negative x component of the spot you're at, and the z component is the negative of the z component. So what I'm seeing here, let me see if I can get this oriented reasonably. First of all, I notice that I'm only currently looking at z values that are positive, and so all my vectors are pointing downward just a little bit. There's a little bit of negative z component. Certainly more downward when the z is bigger, because then negative z is bigger, so we're pointing downhill more. If I were to continue on plotting this for negative values of z, you would see they'd be all pointing upward to some extent. Okay. Yeah, when I look straight down the z-axis, you get kind of it looks almost like a circular kind of thing happening here. Anyway, vector fields, they, maybe you can even see the uses of them already, but we will, in subsequent videos, talk about more examples and applications, certainly over the next week or so. So one of the things you should do here to get really started on this stuff is to find a good plotter for you to work with. I'm using CalcPlot 3D here to do my three-dimensional things, and this one I searched on two-dimensional vector field plotters or whatever, and I found this one. It's really pretty nice. It uses GeoGebra online, so you don't need any special software for it. On the course page there are links to both of these sources.